Yeah, I mean, yes. Well, it's all right. Yeah. Sorry for
No worries.
yeah, first time in person.
It's not a big deal. Is it possible to make the top this better?
Yeah, you can just switch to tab.
Oh,
Always.
hello, everyone. My name is Suhas. I'm a PhD student at Moin Qureshi. So today I'll be talking about quantum error correction. Specifically, I'll be talking about the work I did at IBM over the last year, in collaboration with IBM over the last year. And then I'll talk about the current research I'm doing in quantum error correction. So this work, 5 proxy networks, it's going to appear in a conference in November, and this work is done by me, 3 collaborators from IBM, Ali, Andrew, and Lev, and it's done and also with my advisor, Moin Qureshi. Okay, so this is an error correction talk, so I'm first going to start talking about errors, but I'm not going to start talking about quantum errors. I'm just going to talk about classical errors first. It's a much easier thing to approach, right? So in classical systems, we actually have error correction for DRAM, or the main memory in your systems. And to correct, any errors we have in DRAM, let's say it's kind of like due to like a cosmic ray flipping one of your bits, we have to have some kind of error correction. Fortunately, the error rate in DRAM is actually very low, around 10 to the power of 8 to the minus 8 or 10 to the power of minus 9 per operation. So we really only need to correct 1 error because that's mostly what we'll have. And if we have 2 errors, we can just detect it and just say, let's just crash the system and restart whatever we're doing. So SegDead, this single error detecting, double error detecting code requires you to encode 8 physical bits into 4 logical bits. And this is pretty good. It's about 50% efficiency. Now let's go over to the quantum side of things. I think everyone knows here that quantum computers have errors. And to detect errors on the surface code, most people use something what's called a surface code. And now if I wanted to just detect and correct a single error with the surface code, I would require 17 physical qubits to make 1 logical qubit. This is a little bit worse than SegDead in classical systems, but you may say, okay, this is fine, just 17 is okay. But the issue is in quantum computers, the error rate is so high, we can't just tolerate 1 or 2 errors. We actually have to tolerate something more like 10 or 12 because the operation error rate is so high. And for any promising application, let's say you want to break your friend's RSA key or something like that, you're going to need about 1,000 physical qubits per logical qubit. And this distance number I have, this D number I have is something called a distance. The distance kind of tells how many errors I can actually correct. And here, the number of errors you can correct is just the distance divided by 2. So here you can correct 12 qubits if you give me about 1,000 physical qubits. So this is kind of one of the big issues with the surface code. If I ask you to give me 1,000 physical qubits per logical qubit, and my program requires something like 10,000 logical qubits just to perform, this is actually not a very scalable thing to do, right? Because now I need something like 10 millions or hundreds of millions of physical qubits. There's significant engineering challenges with building a quantum computer this big. So can we do better? Let's first talk about why the surface code is so promising. I just told you that there's such significant investment. I'll give you 3 reasons. First is that it's rather easy to implement. If we look at the local connectivity of the surface code, it's grid-like degree 4 connectivity. And how it's implemented is that you have check qubits in the middle. So you have 2 types of check qubits, Z check qubits, which can correct X errors, and X check qubits, which can correct Z errors. And you have these data qubits. And each data qubit is connected to 4 check qubits, and each check qubit is connected to 4 data qubits. So this grid connectivity is very easy to implement in superconducting processors. The second reason is easy error detection. If I ever need to detect an error, I can just perform a CNOT between one of my data qubits and the check qubit. I'll measure my check qubit and I'll get a bit. This is called a syndrome. My syndrome is 1. I know some error has occurred, so it's actually very easy to detect errors on the surface code. I don't also want to detect errors, obviously. I also want to correct them. And error correction is also rather easy. I can run the minimum wave perfect matching algorithm. There's 50 of these implementations out there. Many of them are fast. And I can use this to figure out what error has occurred on the surface code and then go remove that error. So really, one of the reasons the surface code has actually been so prominent is that people have been researching everything. And actually now everything may have been hard to begin with, and now it's just really easy. This is the result of about 20 years of research, and Google has actually been able to demonstrate 3 different types of surface codes all within the last few years. Most recently, they were able to demonstrate a distance 7 surface code, and they were able to do real-time processing and everything. So the high cost of computing with the surface code is not really good. And ideally, we want alternatives to the surface code. So let's kind of think about how we can do what exactly we want. We look at the surface code. It doesn't matter how many qubits I really encode. I'm always just going to get one logical qubit. Yes, I can correct more errors, but I'm not really gaining anything if I implement more redundancy. Ideally, what we want is that if I increase the amount of redundancy, I should not only be able to correct more errors, I should also get more logical qubits. And this is kind of the basic concept behind QLDPC codes. If I invest more, I can just correct more errors, but I can also get more qubits. So what are really the challenges with implementing QLDPC codes? Well, the first thing is that they're hard to implement. If we look at the connectivity requirements of a QLDPC code, it's rather dense. You can expect something like up to degree 10 or degree 12 connectivity. This is really hard to fabricate on superconducting processors because of frequency collisions. The second reason it's hard to detect errors. What can happen is that when I'm performing my CNOTs on a QLDPC code, I actually need to perform them in a certain way. So I have to have a certain order to my CNOTs. If I have the wrong order, the bits I get from my when I measure my check qubits can be random. And that means that they're unusable because I can never figure out if an error has actually occurred. Whereas if I have the correct CNOT order, then my results are actually mostly deterministic. Unless I get an error, then I'll get a 1. But most of the time, they're going to be 0. So this is another problem. I need to schedule my CNOTs properly because if I give it a bad order, I'll get some bad syndromes. And the last thing is that error correction is really hard. So in my circuit where I'm trying to measure my check qubit, also known as a syndrome extraction circuit, one CNOT error can actually cause 2 errors on my data qubits, and these errors can propagate to other data qubits, even if the CNOT I use with other data qubits is not faulty. And what has happened is that from one CNOT error, I now have 2 data qubit errors. If I don't know that this has happened, it just looks to me that I have 2 data qubit errors, and I get confused. In reality, then if my decoder doesn't know any about this, I will get an incorrect correction. We think about it like this. If a distance 3 code can correct 1 error, and I have this double data error occur, then what will happen is that my distance is effectively 2, because it's a 2 qubit error, but my code is really only able to handle 1 error. So my decoder has to be aware of that this is happening, but as it stands right now, it wouldn't be. So these so-called propagation errors actually reduce the effective distance of the code. So the goal of the work I did with IBM is to tackle all of these problems for QLDPC. And this is an outline for the rest of the talk. First, we're going to talk about reducing the connectivity demands. We're going to talk about syndrome extraction scheduling, or this challenging error detection process. And finally, we're going to talk about something called 5 qubits. 5 qubits essentially are the way we deal with propagation errors. So first, let's just talk about why high connectivity is bad, right? You mentioned frequency collisions, but let's get into why exactly this is the case. So if we look at a superconducting quantum processor, usually what we do is we assign frequencies to different couplings, and these frequencies are assigned in a way that when I shoot a microwave pulse at my processor, I can perform a CNOT between 2 qubits that are connected. And each of these couplings is assigned a frequency. Now, if we think about a dense processor, right? I have a bunch of conditions on what frequencies the coupling have. Yes, 2 faraway couplings could have the same frequency, but if they're rather near to each other, I have some constraints on what frequencies they can have. So for example, we have 2 couplings with the frequency f2. But since they're so near to each other, what will happen is I will activate both of the couplings. And this is rather undesirable. So this is a faulty processor at the end of the day. So high connectivity actually has poor yield. So we have to reduce connectivity some way, but we also have to be able to entangle our data qubits with the check qubits. And here's a very simple idea. What if we just indirectly entangle my data qubits with my check qubits? Okay, so something like this. I have these triangle qubits, these ASPLOS qubits, kind of in the middle of my check. And I'm going to indirectly entangle my check qubits with my data qubits by performing CNOS with this ASPLOS qubit. Here, the effective degree is 8, but the actual degree of the circuit is at most 4. We look at the internals of the circuit, it looks like it works. If I have an X error, for example, on my data qubit, my Z check qubit will detect it. It will say, okay, you had an error. The issue is still propagation errors, though. If I have a propagation error anytime I'm doing a CNOT, it'll still propagate to my data qubit. My Z check qubit can't correct this because it could only detect X errors. It can't detect Z errors. So this is something I still need to do. Yes?
I have one question. So propagation error is the error that the qubit in A like affects the qubit D.
Yes.
All right. Thank you.
Yeah, so it's just a property of the CNOT. It can also happen with X errors, but the CNOT orientation has to be reversed.
Is it because of CNOT gate?
Yeah, CNOT gate. So one faulty CNOT gate will cause a 2-qubit error, one on the controller target. Another CNOT gate, it doesn't have to be faulty, will propagate this error.
All right, thank you.
So let's use something called 5 qubits. And the basic motivation behind 5 qubits, let's just make a qubit just to detect these propagation errors in my circuit. So here, for example, I'm going to replace all these triangle qubits with these so-called flags. And we're going to separate the role a little bit. My Z-check qubit will only have to detect X errors. My 5 qubit will only have to detect propagation errors. And here, if we look at our new circuit, this is how we entangle our data qubits with the check qubits. And what will happen is that even if I have a propagation error with my data and 5 qubit, my 5 qubit will read out 1 when I go measure it. So now we can finally achieve my effective distance amount. And at the same time, if we even have an X error on my data qubit, I can still detect it using my Z-check qubit. This is ideally what we want. But here's a challenge with 5 qubits. There's 2 things. First thing is that I need decoder support. Now, because I'm measuring both check qubits and 5 qubits, I need to somehow combine them when I'm doing error correction. And this is where we need something called a flag protocol, and we'll discuss this later. But I need to leverage this flag protocol to actually detect propagation errors. If I just measure the 5 qubits and then don't use them properly, I can never actually correct propagation errors. The second issue is I could possibly overuse 5 qubits. So for example, here, this may look fine, right? I have 2 levels of indirection using 5 qubits. But a propagation error, that F1 detects is also detected by F3. This is really redundant information. And the issue of this redundancy as a problem is that if I have any errors on F3, I will get conflicting information because I don't really know what has happened. Has an error happened or has an error not happened? F1 and F3 are ideally supposed to give me the same result. So we ideally don't want to really overuse these 5 qubits. So here's an idea. What if we have a different type of qubit? So let's just use so-called proxy qubits. Instead of having 2 levels of indirection, if I have 2 levels of indirection, anywhere beyond the first level, I'll just introduce something called a proxy qubit. Now, if I do have my propagation error, my proxy qubit won't give me any results regarding that. And even if anything happens, all is good, right? So the benefits of this so-called flag proxy network design, where we have a first level of 5 qubits and higher levels of proxy qubits, is that it's low degree connectivity, it avoids flag overuse, and the effective distance is maintained. So for more details on how these networks are actually constructed, please refer to our paper that'll eventually be out of it. So the biggest challenge with flag proxy networks is actually 5 qubits. These take up quite a bit of overhead. And if we look at the 2 types of QLDPC codes we're looking at, hyperbolic surface codes and hyperbolic color codes, they take up about 50% of the qubits within my flag proxy network. This is rather steep. Keep in mind, all I had to begin with were data qubits and parity qubits or check qubits. Right? These are actually not that much. These are actually not too much in terms of overhead. So ideally, we want to kind of reduce these 5 qubit overheads. So here's the key insight. Many checks share pairs of data qubits, as we do have here. Both of the checks share data qubits, but they're using different flags to interact with each of these data qubits. So here's an idea. Let's just optimize our flag assignments so that every time we have a pair of data qubits, we're actually sharing flags between checks. So it looks something like this. That way we can actually significantly reduce the flag overheads by about 10%. So now I'm going to talk about, like, okay, are these FPNs actually efficient, right? In theory, QLDPC codes can be as much as 100x more efficient than the surface code, but what happens if I actually have to implement it in hardware? These pesky things like flag qubits and check qubits, they kind of increase your overheads. So if we look here for both of these types of QLDPC codes, on average, these codes are actually 2.4x and 4.6x respectively more efficient than the distance 5 surface code. And keep in mind, this is a distance 5 surface code. This is actually one of the more efficient surface codes. If I increase the distance over time, my improvement will increase quite a bit. By the time I reach distance 25 or so, my benefit is probably going to be about 100x. So now we've talked about, these kind of flag proxy networks and how they're so much more efficient than the surface code. But we just have a bunch of qubits on a processor, right? Now we actually have to be able to detect errors using this kind of network. And this part of syndrome extraction scheduling is rather involved in terms of math and all that. I'm not going to go too deep into the math, but I just want to kind of give an intuition of what the constraints are for syndrome extraction scheduling and what we did. So this part of this talk is obviously how do we detect errors. And what's going on here is that I have two check qubits, a Z check qubit and an X check qubit. Both of them are, have to entangle with 4 data qubits. So in total, I have to perform 8 CNOTs. And I have 8 different time steps in which I can perform these CNOTs. So I have, roughly 8 to the 8 ways to order CNOTs. If you were to, I think this comes out to about 16 million possible combinations. For this code, it's, brute forceable. If I have a very large code with hundreds of checks, it suddenly becomes not so feasible to brute force. But but ideally, I want 2 things. I want my CNOT circuit to be correct, and I want it to be low down. In this example I given here, it's a very simple one. I'm going to do all the CNOTs for my Z check qubit first, and then do all the CNOTs for my X check qubit next. This is functionally correct, but the issue is that this is a high depth circuit. Okay, so let's try to reduce the depth a little bit. It's not so easy, because in the next circuit I've given, it's not functionally correct, but at least it's low depth. So we're getting closer. And the final circuit I'll give you is a functionally correct and low depth circuit. So this bottom one is ideally what we want. And the challenge here is that amidst this exponential number of possibilities for my CNOT order, I got to find a needle in the haystack. So scheduling is actually just NP hard because there's so many possible options. And there's 2 constraints here. The first one is uniqueness. 1 qubit cannot perform as CNOT, 2 CNOTs at the same time. This is rather straightforward, right? In most processors, you can't do this. The second one is a little bit more on the code side of things, and this is commutativity. Essentially, when I'm measuring my checks, I need to make sure my CNOT order is such that my 2 checks don't anti-commute. As most people here may know, X and Z gates, they anti-commute with each other. I can't just interchange them. And it's the same idea here with X and Z checks. So the issue here is that when I try to encode these constraints into a solver, and I have, let's say, hundreds of qubits or thousands of qubits in my code, the amount of constraints is too much, even for like state-of-the-art solvers like IBM's CPLEX or Gurobi. So we need to somehow be able to find a schedule despite these kinds of overheads. So let's just think about, okay, how can we approximate this? And here's a simple greedy algorithm. I can't use my solver on the entire code. So how about I just use it on each part of the code every time? And here's the basic idea. I'm going to go through and schedule each of my checks individually. And I'm going to figure out, okay, when is my data qubit going to do a CNOT with my check qubit? So here's an already scheduled check, and now I'm going to move on to a new check. Here, this check shares 2 data qubits with my existing already scheduled check. And now here, where we have 2 common data qubits, I need to enforce commutativity constraints. And then once I schedule this blue check, I'm going to move on to this unscheduled check. This greedy algorithm reduces about 2 to 6 CNOTs on average. And the benefit of this is that, yes, I decrease the amount of CNOT error I have in my syndrome extraction circuit or error detecting circuit. I also decrease decoherence and dephasing error as well as idling error. So it's actually a threefold improvement just by decreasing just a few CNOTs. Now I'm going to finally talk about the last part, which is how do you even correct errors? I've talked about, okay, we can get syndromes. We can figure out what errors have happened. We can put qubits on a processor. Now I actually have to go deal with these propagation errors I've been talking about so much. So in decoding, we have something called error events. And usually what decoders do is that they're going to operate on these error events, and each of them have some probability. The idea is that I'm going to choose a configuration of error events that is most likely to have caused my syndrome or my check qubits to flip. And here's the common case. The common case is obviously going to be I don't have any flag bits flip at all. And this is probably as simple as something as like a data qubit error. For example, in the color code, a data qubit error will flip 3 check bits. You could also have a measurement error you can also have a measurement error on your check qubit. Let's say the first time you measure your check qubit, you get a 0, and the next time you get a 1. You have to also be able to handle this, for example. And then there's the uncommon case, which are the flagged errors. So for example, I could get my same 3-bit error, but I have a flag attached to it. I could have a multi-qubit error, just like in propagation errors, with the flag attached to it. Or I could have a very complex error pattern where I have 2 qubit errors, but I flipped a bunch more bits and I have multiple flags attached to it. These are some of the examples of flagged errors, but really flag qubit error events are actually very diverse. And handling all of these kinds of events is a big challenge. So let's first think about how we should leverage flags, right? So in my prior example, you could have an error event, and you can have the same error event, but flag. Here's an example, right, where we have the flagged error event of a propagation error, 2-qubit error, and we also have just a normal 2-qubit error. This is not a propagation. And each of these will have different probabilities, right? Just 2 errors happening is just going to have a probability of p squared, where p is my error rate. If I have a flag, then I know a single error has occurred, a single CNOT error, and I know the probability of this error is about p. So when I have a flag, I should ideally correct for my propagation error like this. And what I'm going to do is when I'm trying to estimate the probabilities of what has occurred and what hasn't occurred, I'm going to check if my flag has been measured 1, and I'm going to choose the correct outcome. So if my flag is measured 1, I'm going to choose my flagged error event. If it is not 1, I'm going to choose my non-flagged event. And then I want to send this to my decoder, and then it's going to give me the most probable error. That's ideally how decoders should leverage flags. But the challenge with selecting flag events is that you can have a lot of overlapping events. And here's 2 examples. You can have the propagation error I've talked about before. You could have another propagation error, this time 3 qubits, where I have 2 flags flip. And here the overlapping thing is that I have the common check qubit and I have a common flag qubit. And now it's suddenly a bit more difficult, right? What happens if I have F2 flip to a measurement error, or what is more common here? And now I have to kind of weigh these kind of probabilities. Like I could have errors when I measure my flag qubit and all these things, and I may have to make a decision. So here's a really simple idea. I'm just going to group all of my error events by the check qubits, the check flips, right? Yes, I could have different outcomes depending on what check the qubits have flipped, but at least I can now kind of categorize them, right? What am I going to do if I see these 2 check bits flip? So we call this an equivalence class. And what we're going to do is exactly the same thing as before. We're going to look at our flag syndrome, and we're going to compare all these and choose the most probable event to use while decoding. The benefit of this strategy is this flag protocol is that it's distance preserving. So now we've fully recovered our effective distance. And it has comparable error. And with this strategy, the hyperbolic surface code and hyperbolic color code actually have comparable error rates to our normal surface and color codes, which is actually quite impressive because a lot of people didn't think this was possible. So here's the conclusion of this part of the talk. We have QLDPC codes, which are an efficient alternative to the surface code. But the issue with these QLDPC codes is that they're limited by this dense connectivity, which is hard to fabricate on superconducting quantum processors. You have challenges of syndrome extraction scheduling, which prevents detecting errors rather easily. And then it's also rather hard to deal with propagation errors, which harm the code distance. So to tackle these three challenges, we proposed flag proxy networks as a very simple architecture for putting out a QLDPC codes on superconducting hardware. We have a very greedy algorithm for computing these syndrome extraction circuits. And we have a generalizable flag protocol for decoders so we can handle these propagation errors. And one of the key outcomes of this work is that we find that these FPNs have comparable error rates to the surface code and color code, but also having degree 4 connectivity, which is the exact same as the surface code. Any questions about this part of the talk before I move on?
I have a question. So the greedy syndrome extraction scheduling algorithm, does that take advantage of the superconducting hardware at all, or could that be improved to take advantage?
So what do you mean by take advantage?
Like, because like compared to like trapped ion and neutral atom computers, they'll say like, oh, we can move our qubits around and we can achieve better connectivity without going an extra step like this. But is there any way that you can modify this, the method that you've proposed here, to take advantage of superconducting topology?
So I see what you're saying. So one of the things about superconducting qubits is that, so at least about these FPNs, is that everything is local.
Okay.
So any qubits I perform interactions with, I'll always have a coupler. So if we look at, for example, here, right? These are all couplings. I'm never going to have a qubit one perform an interaction with something it doesn't have a coupling. Now, regarding what kind of support you need from your superconducting hardware, one of the big issues about QLDPC codes in superconducting computers, at least, is that they're non-planar. Okay. So I can't manufacture them with existing superconducting hardware. But what I will need is another layer on top of that where I can have long-range couplings.
Yeah. Okay.
I haven't really talked about that here because everything is biplanar for these codes, and it's really not interesting to talk about. But that is a consideration.
Yeah. Okay.
Yes.
How do you actually decode the syndrome? Do you believe propagation or?
So we don't use belief propagation because the reason we actually chose hyperbolic surface codes and color codes was that so we could have something to build off of, because we tried to use the same decoders for surface codes and color codes onto these hyperbolic codes. Other codes like such as IBM's bivariate bicycle codes, which is like the big one they were advertising earlier this year, those use belief propagation. So it depends on the code what you use. So a surface code decoder is different from a color code decoder, for example. Any other questions?